exercises together, but before we do that, I want to just take a look at our schedule, just to remind you where we are. We're going to talk more about functions and their graphs today, and the next thing that's coming up is quiz 2, but that's not till March 9th. Okay, take home quiz 2. And we've got a project 2, but that's not, oh, that's going to be due March 16th, and I will give that to you sometime next week, probably. All right, so let's look at our preview exercises. So we're just finding the equation of some lines. So this is material that you should know from a previous class. You might be a little rusty, that's okay, but as long as you can refresh your memory and this looks familiar, you'll be all right. So I'm just going to find the equation of this line first, the first line. So in order to find the equation of the line, typically we need 2 points. So this point right here has coordinates 0, 2. And the typical equation of a line that we use is y equals mx plus b. You might also be familiar with another form, point slope as opposed to point intercept, slope intercept. You can use whichever one you like. I'm going to use y equals mx plus b. It's a more common one that people know. So the things you have to figure out are m and b. X and y are just part of the equation. They'll always just stay x and y. You just have to figure out what m is and what b is. So m is your slope, right, which is rise over run, or you can think of it as change in y over change in x, vertical change over horizontal change, which basically just means subtract the y coordinates and subtract the x coordinates. So I'm going to do 8 minus 2 over 20 minus 0. That comes out to 6 over 10, which is 0.3. Sorry, 6 over 20, which is 0.3. Okay, so now I know the slope. So when I have my y equals mx plus b form, now I can replace my m with a 0.3. And then in the equation y equals mx plus b, m is the slope. What is b? The y-intercept. In this particular example, it's nice because I can see the y-intercept on my graph, right? It crosses the y-axis at 2. So I'm just going to replace the b with a 2. So I have y equals 0.3x plus 2. So there's the equation of the first line. All right, let's think about the horizontal line. There's 2 points on that line labeled. They have something in common. What is it? They have the same y coordinate, which is 8. So the equation of that line is super easy. It's y equals 8. Every point on that line has a y coordinate of 8. So that's how we identify that line. Y is always 8, so y equals 8 is your equation. Does that make sense? Not even any calculations to do. All right, let's look at the last line here. 30, 8 to, what are the coordinates of this point here? 50, 0. Okay, so I'm going to do the same thing I did before, find rise over run to get m. So m is going to be 8 minus 0, subtract the y's, over 30 minus 50, which is what I get when I subtract the x's. So I get 8 over negative 20, which is negative 0.4. Okay, so now I have the equation y equals negative 0.4x plus b. It's not quite as obvious from this picture what b is, because you can't see where it crosses the y-axis. So how can I figure out where it would cross the y-axis? Plug in the coordinates of a point. You can use any point you want. Okay, so I'm going to plug in 50, 0. 50 is an x coordinate, y, 0 is a y coordinate, so I plug in 50 for x and 0 for y. So I get 0 equals negative 0.4 times 50 plus b, which I don't know, And now I have an equation where the only thing I don't know I can solve for. Okay, so B ends up being, to take 0.4 of 50, I could take 0.1 of 50, which is 5, and multiply it by 4, which is 20. So I get negative 20, add it to both sides, B is 20. So my final equation is going to be y equals negative 0.4x plus 20. It's jogging some memories. We shaking the rust off. Okay, good. All right, so it's just finding equations of lines. All right, so today in class, equations of lines are going to be important. We're going to have to be able to do that. But what we're actually going to talk about are something called piecewise functions. And that's when a function needs more than one formula to accurately model a real life situation. Okay. For example, think about taxi fares or the US tax code, late fee charges on a credit card. They all require a function that uses more than one formula. It's in some instances you use one formula, and in other instances you use a different formula. So here's an example where this graph that we were just working with, it represents the amount of water in thousands of gallons in a swimming pool after T hours have elapsed. Okay, so I've added some labels to my X and Y axis. So my X axis is now time in hours. Y axis is thousands of gallons in the swimming pool. Okay. So if I'm just looking at the domain 0 to 50, from 0 hours to 50 hours, what has happened to the amount of water in the pool in that time? Increased, leveled off, and then dropped. Yep. Good. So over what interval was the water increasing? 0 to 20, right? Remember when I ask you over what interval, I'm asking about the horizontal inputs, in this case, time, right? So we would say from 0 to 20. And remember from last class that when you explain when something is increasing or decreasing, you don't include the endpoints, because at those endpoints, we say it's neither increasing or decreasing. So on what interval is the water level constant? 20 to 30. So, and again, don't include the endpoints, because it's unclear whether it's increasing or constant at 20, right? So some textbooks say it's both, and some textbooks say it's neither. Our textbook goes with the neither approach, so 20 is not included in either interval. Neither one is really wrong, but we're just going to go with the convention that our textbook uses. And then what interval is water level in the pool decreasing? From 30 to 50. 30 hours to 50 hours. So these three intervals define three different pieces of the domain where very different things are happening. So we have to write different formulas to describe what's happening on these three different pieces of the domain. So this is the notation we use to represent the function for the pool. There are three different time intervals, so three different formulas. So we start by naming the function, g of t. That could be like gallons at time t. Maybe that's why we called it g. All right, and then you have to put a big curly bracket, which notice we don't close, right? So it's just a weird, just open a big curly bracket. Then you list the three different formulas that we found in the preview exercises, right? So 0.3t plus 2, 8, and negative 0.4t plus 20. So g of t is holding the place of the y equals, right? That's like my y. I don't need to write y equals in each of my formulas. And then after each formula, you write the word if and give the interval on which that formula applies. Okay? So the 0.3t plus 2, that formula applies only from t equals 0 to t equals 20. Okay, and then the 8, y equals 8, that applies from 20 to 30, from time 20 to time 30. And then y equals negative 0.4t plus 20, that applies when? 30 to 50. 30 to 50. And I included, so where you include the endpoints on a piecewise defined function is pretty arbitrary. Okay, so in this case, the formula for this line and this line give you the same point when t equals 20. So you can include it in either location with either formula. So I included the 20 with the first formula. So then I did not include it with the next one. I included the 30 with the 8, so I'm not going to include it in the next one, and then I'll include the 50 in the last one. There's nothing technically wrong if you include this in both, if you include the 20 in both of those formulas. It's just kind of like bad grammar, right? Because we know that a function can only have one y value for any given x value. So it's weird to plug in 20 twice, right? Because we know that when you plug in 20, you should only get one y value. So why would I plug it into two different places, right? If it's always going to give me the same thing. So we don't use it in both places, the or equal to. There's nothing technically wrong with it. It's just weird to write it down that way. All right, so that's an example of a piecewise function. We need 3 different formulas because the pool is doing 3 different things. Here's another one. A cell phone plan with Verizon Wireless might charge you $79 per month, and you get 700 minutes for that $79. And any minutes over 700 gets charged at 45 cents per minute. So if C is your monthly cost in dollars and M is the number of minutes you use, let's see if we can calculate the cost for 535 minutes. $79, right? Right, 535 minutes costs $79. How did I know that 535 was representing minutes in that problem? Yeah, so the C represents cost. It's in parentheses, which means it's an input. Good. All right, what about the cost for 850 minutes? Yeah, so you have to pay your base $79. And then we went 150 minutes over our allotted 700. So we have to subtract, right? 850 minus 700. I know I'm writing this out in excruciating detail, but you'll see why when we get to the next part. So we had to subtract to figure out how many minutes over we went, and then for each of those minutes over, we multiply by 45 cents, right? So that comes out to the extra 67.50, $146.50. Does everybody see where we got that number? Okay. So my interpretation is that 850 minutes costs $146.50. All right, so I'd like to use a piecewise function to represent the cost of a cell phone plan, because there are 2 different situations, right? You get charged a certain amount if you are 700 minutes or less. You get charged a different amount if you're over 700 minutes. So I have 2 different formulas that apply to figuring out the cost of my cell phone plan. So the easiest formula is that it's going to cost me $79, right? So I'm going to put a 79 here. Cost for m minutes is $79 if what? Super close. If m is less than or equal to 700. M is representing number of minutes. M less than or equal to 700. Good. All right, and then the other formula I'm going to have is my base formula of 79 plus however many minutes I go over 700 by times 45 cents. So what am I going to put in parentheses there to represent how many minutes over 700 I went? Anna. M minus 700. You got it. Yeah. So you take M, the total number of minutes you talked, subtract 700 from that, and that's how many minutes over you went. So this is M minus 700 goes in there. Times 0.45, 45 cents for each minute over. Okay. And then that formula is used if what? M is greater than 700. So there's another piecewise function, right? It's different formulas on different parts of its domain. And it takes a little bit of getting used to the notation, but it'll become second nature. Questions so far? All right, so in my two examples, the first one I gave you a graph, right? And we wrote a formula for it, right? And then in the second one, I gave you a verbal description of a function and we wrote a formula for it. Now I'm giving you the formula. I'm giving you the formula and I want to draw its graph. Okay. So my two formulas are y equals x squared and y equals 1 minus x. Okay, so I've got two different formulas here. That f of x is holding the place of y. It's representing y for both of those equations. So I have two different formulas, and I have to graph them. Anybody know what x squared looks like off the top of their head? A parabola, right? Let's say you didn't know what that equation looks like off the top of your head. What would you do? Yeah, you just pick some x's, get the y's, plot them. Yeah, so you can always plot by getting some points. So I'll make a little xy chart, and maybe I'll do like -2, -1, 0, 1, 2, 3. Right? And if y is just x squared, square your x's and you get 4, 1, 0, 1, 4, 9. So I'm going to plot those points. -2, 2, 3, 4. -1, 1, 0, 0, 1, 1, 2, 4, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, and I also have that at -3. Okay, so that's y equals x squared. I'm just going to graph that, the whole thing. All right, so I've graphed y equals x squared. Now I'm going to graph y equals 1 minus x. You might be able to do that by knowing how to graph a line. That's just a line that has slope -1, y-intercept 1. But let's say you didn't know off the top of your head, you could just plot some points, right? Pick some y's like 0 and 3 and -2, random x's, and then plug them in and get the y's. So 1 minus 0 is 1, 1 minus 3 is -2, 1 minus -2 is 3. So we get some points, we'll plot them and connect them. So 0, 1, 3, -2, and -2, 3. And those form a line. So I graphed two different equations here. But I have completely ignored the if part of my piecewise function. I'm only supposed to graph x squared for x's that are smaller than 1. And I'm only supposed to graph 1 minus x for x's that are bigger than or equal to 1. So the dividing line here is at x equals 1. So I'm just going to put this in for my own visualization. Which one of these graphs do I want to keep to the right of the green line? The purple or the pink? Yeah, which one am I keeping if I'm to the right of the green line? The pink, yeah. So x is bigger than 1. That is the right side of the green line. X is bigger than 1. So that means keep the 1 minus x graph, which is the pink one. So I'm going to erase everything purple to the right of the green line. And even on the green line, I'm erasing the purple. So I put an open circle at the end of that to indicate that I am not drawing the purple graph at x equals 1. Now to the left of the green line, which is x equals 1, I want to keep the graph of x squared, which is the purple graph. Right, so I'm only supposed to graph purple when I'm to the left of the green line. So I got to erase all the pink. Try to do my best to do a surgical removal here. Oh well. Oh, it's supposed to be purple. Okay. And then pink is supposed to be at 1 should be 0. So that should be an open circle right there. No, that should be pink. There we go. Okay, so I just erased everything in the spots where they're not supposed to exist. So when I'm done, I should be able to read this and say, okay, I graphed x squared when x was smaller than 1. So to the left of x equals 1, I have a graph of x squared. To the right of x equals 1, I have a line 1 minus x. And then I have an open circle and a closed circle depending on whether I have a less than or greater than or equal to. Right? Does that make sense? The open circle and the closed circle? Okay, good. The open circle means do not include that point, right? So in this case, x squared, I'm supposed to graph only when x is smaller than 1, not or equal to. So right at 1, I put an open circle on the graph of x squared to mean do not include that point. And on the 1 minus x, I put a closed circle because I do want to include the point because it's or equal to. So I include it on that one. Okay, so I'm going to have you work on some activities dealing with piecewise functions. Each of them have a description of the function, and I want you to both sketch a graph and write an equation. For some people, it's easier to graph it first, then write the equation. Some people, it's easier to write an equation and then graph it. You can do either order. And I just want to warn you that when you get to the very last one, as taxes tend to be, it is very complicated. So this is sort of an extra challenge. And if you can't get it, don't fret, right? I will never put something that complicated on a test, right? It's just there for your own interest, right? If you're interested in how taxes work.